Okay, welcome to lecture 8.6. By the way, I just messed up in the last session video. I said this was going to be 8.5 and I wasn't 8.4, but I was an 8.5 and this one is going to be 8.6. Oh, man. If I say a number, give a number to these sessions, uh, just ignore it. It's probably wrong whenever I say it. Okay, so here is the McKelvey-Palfrey paper. So far in this course, everything we've done has been decision theoretic. Every structural model that we've had involved only one person making a decision. So we haven't had a situation where it's two people playing a game against each other. And now we're finally going to do that. Okay. So, first little background. I put on the syllabus the paper by Bresnahan and Rees. So you might want to read it, but the key is that really kind of Bresnahan and Rees were kind of the first to do this, to say, let's put in some structure, let's have a game theoretic model and try to estimate parameters from that game theoretic model. Now, one problem, they did this, they were looking at like duopoly problems, and I think the data they were going to get is like small towns where there's two gas stations. And the problem is, so they set up their theory, and then they add an error term to various outcomes. And then the problem is that, say you make the error term normal, and one problem with the normal is that it's infinite tails. And so the Bresnan and Rees, they set up this game and they would say, well, it looks something like a prisoner's dilemma, okay, by the parameters we have. But then you add on these error terms. So in a non-stochastic world, the game would have been something like a prisoner's dilemma. But then you add these error terms, and then over some ranges of the error, the game indeed looks like a prisoner's dilemma. But once it gets so big, all of a sudden, what looked like a prisoner's dilemma all of a sudden starts looking like Matching Pennies game or some other game. And so the qualitative nature of the game changes, including, like, depending on the value of that error term, it can go from having one equilibrium to many equilibria. And it's not clear that Bresnahan and Rees really got any results on it. It was kind of a mess. And, they deserve credit for making the attempt. Now, what McKelvey and Palfrey do is they say, well, let's, again, look at some games. And they're going to do an assumption that some people will call ad hoc. And I'll show you that assumption in a second. And some people might criticize him for it, but I'm not. If you don't make that assumption, you don't get any results. Okay, so, and it's not that ad hoc, say that, but anyway, I'll show you the assumption in a second. So, okay, but this paper is fantastic. That fantastic paper. I'm probably not supposed to say this, but I'm on this committee that's something like 200 to 400 people. I don't know. I mean, it's of economists who nominate people for the Nobel Prize, and it's a huge committee. So I don't think they really pay attention to who I nominate. But every year, McKelvey has passed away, but I nominate Palfrey every year. So I think his other work is great too. Actually, I nominate a few. Plot and another guy, Dave Barron. I nominate the three of them every year. I say for their work in political economy. But really, Palfrey also deserves work in this paper. In this paper, maybe alone, he deserves a Nobel Prize for it, I think. If you can understand it, I think you can. I think the beauty of my class is that you have a teacher who's pretty smart, but not near as smart as Palfrey and McKelvey. I'm smart enough to understand it, but I'm not near smart enough to have written it. Um, Now, what that means is you ratchet down the intelligence level. I'm able to translate it to the mortals. So Palfrey and McKelvey, I don't think they could. I don't think the average person can even understand that paper. So, but if you get someone who's a little stupider, who has like slogged through it and tried to understand it, and then he can present it, I think so. I think that from the lectures you'll have from me, you have a great opportunity. You can understand this great paper, and I think there are lots and lots of ideas out there to which you can apply this technology, and not that many people understand it. It makes a great job market paper if you can do it. I think there's maybe half dozen to a dozen at most uh, PhD grad students who understand this paper and can do it every year who graduate. Um, okay, so here's how. Let's see. So before I get into kind of the so by the way, right now, so this session, I'm not going to go into that many details. I'm going to give kind of an introduction and then explain how to read the paper. All right, first, introduction for my introduction. I want you to consider the Ox game. So OCHS Ox 1995. So this is McKelvey and Palfrey. They review the paper. Now the key is the Ox paper. So that's an experiment, and in the experiment there are two players, A and B. So A and B, and then so A has two actions. Play A1 or A2. B has two actions, B1, B2. By the way, this is going to look like matching pennies game. Okay. So in fact, let me start off. Suppose that these are the payoffs. 1 0 0 0 1 0 0 1 0 1. If instead we called this A1 heads, B1 heads, A2 tails, B2 tails. This is exactly matching pennies. And A wins on the matches, wins $1 on the matches. So if they go heads, heads, or do tails, tails, A does tails, B does tails, A gets $1, B gets 0. On the other hand, if they don't match, B gets $1, A gets 0. Okay. All right. Now, so for this class, you don't have to know game theory, but this is something you need to look up on Wikipedia if you don't know it already. So you need to look up on Wikipedia and go through some examples where you can calculate the mixed strategy equilibria for some of these two action games. For two people, each player has two actions. You need to know that. So you need to know how to calculate a mixed strategy equilibrium. All right. Now, assuming you've done that or have already taken a class in game theory, we all know in the matching pennies game, there's only one equilibrium, and there are no pure strategy equilibria. There's one mixed strategy equilibrium, and it's where both play heads or tails 50-50. Okay, and that's would be the equilibrium to this game. A plays A1 50% of the time, A2 50% of the time, B does the same thing. Okay. Now, here's what Ox does. He says, okay, let's take this game. Let's make one little change. Instead, where A gets a payoff of 4 from playing that game, from playing A1. Before it was 1, now it's 4. Okay, so A gets a little bit more, or a big chunk more, if the outcome is A1, B1. Okay. I think most people's intuition is to say, well, if you change the game that way, A is going to rationally play A1 a little bit more. Okay? Instead of playing 50-50, he's going to play A1 with a little bit higher probability. Okay? That's the intuition. That's my intuition. It turns out that's what they got in the real experiment. But that's not what the mixed strategy equilibria predicts. And here's the key thing to think about. If you've studied these mixed strategy equilibria, you have to pick a mixing strategy that makes the other player indifferent between the two actions. That's the key. So the only way B is going to mix is if he is indifferent between the two actions. And the only way A is going to mix is if she is indifferent between the two actions. So the key is B has to pick probabilities to make A indifferent between A1 and A2. Okay? A has to pick probabilities to make B indifferent between B1 and B2. Okay? Now, here's what's going on. B's payoffs have not changed at all. Okay? So if A has to continue to make B indifferent, A has to keep playing the exact same probabilities that she did before. She has to continue playing 50-50 among A1 and A2 to make B indifferent. Because B's payoffs have not changed. Okay? So B's payoffs has not changed. That means A's mixing strategy can't change. So A has to still play 50-50, even though A gets a higher payoff from this A1. Okay? Now, B is the one who's got to change. So B, all of a sudden, I guess, has to play B1 less. So he's got to make A1, A indifferent between A1 and A2. So I guess B has to play B2 more often. Okay. So, in fact, here's what the mixed strategy equilibrium. So this is the theory. This is from just game theory. This is what Nash would tell us. It says that B should play B1 with 2 probability. Okay, before it was 50 when that was a 1. Now it's when that was a 1, B was playing B1 with 50% probability. Now it's only 20% probability. And then so he'd play B2 with 80% probability. Meanwhile, A should play A1 with 0.50 probability. Okay. So that is the theory. Okay? That's what John Nash is taking his, first paper as his famous theorem. That's what it predicts. Okay. What happens? So, actual play in experiments. And this is from Ox in the 1995 player. B plays B1 with approximately 0.34 probability. Okay, so it goes in the right direction. A plays A1 with approximately 0.55 probability. Okay, so the actual play, I think, is consistent with the intuition I described at first. You increase A's payoff for the A1, B1. You think, oh, okay, I'll play that more. That's what happens in the actual experiments. Maybe it wasn't that much. 0.55 is not that much higher than 0.5. I don't know. But anyway, our intuition, or my intuition, predicted the direction correctly. The theory did not. Okay? So here's what's going on. So there's a number of experiments like this where the experiments didn't quite match what we would expect from the game theory. And McKelvey and Pallifer are going to say, I think we can have a framework that explains a lot of these experimental results. Okay, and then later, the next session, we'll say maybe we can use this even for not just experiments, but I'll call it real data. That's not fair, but data, non-experimental data. That this McKelvey-Palfrey model may actually also explain a lot of results in those cases. Okay, so that's the OX experiment. Okay, by the way, so this is where I'm getting those numbers. Here is from the paper. This is from the McKelvey-Palfrey paper. You'll notice there's 5 black dots on that. So what's going on, they ran this a whole bunch of different trials, something like 100 trials, but then they grouped something like 20 of them. The first 20 is one group, and the second 20 is another group, and each dot represents an outcome from that group of trials. And so if you see, it looks like you take on the y-axis, the average is about 0.34. Okay, that's where I said B plays B1, about 34%. By the way, the horizontal axis, okay, that's what we're going to talk about. So this is, we're going to talk about a lambda that McKelvey and Palfrey estimate. Okay, we'll get to that in a second. Then you notice the plus marks. There's one outlier over here. By the way, these two, I think that was the one case. I think that was the final group. So if they did something like ran the experiment 100 times, set them in groups of 20, 5 groups of 20, I think that was the 5th one where people had a little more experience at it. So for what it's worth, if you're an experimentalist, that case shows what happens when people are a little more familiar with the experiment. The others show what happens in the first groups of trials. So each dot represents what A did in the various groups, and you'll notice if you project those to the y-axis, you get about 0.55, the average of those marks. Okay, so that's where is that right? Maybe 0.53, maybe 0.54. I'll let you decide. Okay, so that's the OX experiment. Okay, you know what? I've gone 17 minutes. Okay. All right, that is a bit of the setup, a little motivation for what's going on. Let me do one more session. I'm going to end that. So 8.6, I can't remember. So this is the end of that session. The next one, I think this is 8.6, and so I'll see you in 8.7. Okay, see you there.